Okay, so can everybody hear me? Is this a little better with the microphone? Much better, huh? Everyone in the back, can you hear me? Does it need to be louder, or is that good? It's good. Okay, so we have small improvements, or maybe the microphone's a big improvement. We have a microphone, we also have, I have the old-fashioned pencils, so they're going to maybe show up darker when I write. Some announcements. Your homework is due on Thursday, your first homework. If you haven't started it, you may have an interesting couple of nights. But it's due on Thursday at the start of class. And you have your project proposals due next Tuesday. And on the course website, in the homework section of the website, we've put up a little kind of outline for what the proposal should be. It's just the same information that Jeff gave you in class when he talked about it a couple weeks ago. So don't let that kind of slip your mind either, because that's important to start thinking about that stuff. So are there any questions that people have before we start lecture? Are people confused about something? Are there lingering issues in the last couple of lectures? You can't be totally clear about everything. I know I've confused myself a couple times. No? Okay. So last time we talked about subgradients, which for many people I think was a new topic. I'm going to review the definition of subgradients for you. We talked about convex functions, and for a convex function, a subgradient, we talk about a particular point x to be any vector that gives us a linear underestimate of the function. Okay, so it's any g such that f of y is bigger than or equal to f of x plus g transpose y minus x. Yeah?
Sorry, you mentioned questions from my lecture. In last week's lecture was said that you take any element of the subgradient to your step. Is there anything, suppose you could, for free choose any element set by any constraint, which one would you choose? Would you choose anything that was smallest magnitude or something like that?
That's a good question. So the question was, in case everyone didn't hear it, if there's more than one subgradient, when do you choose like that subgradient? Which subgradient do you choose? So there's kind of two types of subgradient calculations, or subgradient calculus. There's strong calculus and weak calculus. Strong means that you're able to compute every possible subgradient of the function. That's pretty rare. Usually you can't do that. A lot of times, or that's pretty hard. A lot of times you only compute a couple subgradients easily, or just one. So there won't be a lot of cases in which, well, I take that back. In many applications, you won't be able to compute more than one easily. So you just take the easiest one to compute. If you have more than one, that's kind of a subtle question. Sometimes, let's see if I can think of an example. So if you think about subgradients of the infinity norm, then any element that doesn't achieve the maximum, the subgradient can be anything between 0 and 1. Or say even the absolute value function. Right? If the absolute value is 0, then it can be anything between -1 and 1. Sometimes you might think it's actually helpful to put a little bit of randomness in the program and actually take a number uniformly at random between -1 and 1 as the subdifferential for that particular component, and not just take 0. So it depends on the application, but sometimes people do things like, if they're able to compute more than one subgradient, they might add a little bit of randomness in. If you can take anything over an interval, but take something uniformly at random with that interval to kind of get rid of worst case situations. The theory that we have, it holds for when you take any subgradient. We're not talking about choices of subgradients. And in fact, we're going to be talking about the case in which you don't have control over which subgradient you get. You just get a subgradient. That's what our subgradient method is. So it's a worst case bound for that situation. And we're going to see at the end of, probably at the end of this class, maybe the middle of this class, that can kind of hurt you. If you don't always get a choice of which subgradient to take, which is often the case, then what we've done is basically the optimal rate. You can't do better than what we've done. Yeah?
Can you use guidance similar to backtracking for subgradient?
No. So for the subgradient method, we're going to go through and review that just in a bit. But for the subgradient method, the convergence is all kind of using these fixed step size rules. So the step size choices are not adaptive. Remember, we had a fixed step size that we had it bound for. We also had a diminishing step size we had it bound for. People don't use adaptive choices for subgradient method as far as I know. Do you know any different?
You can't usually do a line search, right? So you can't, right, because the subgradient is guaranteed to be a descent direction. And so adaptive, like the usual way of getting an adaptive choice just isn't applicable.
Yeah. So good questions, though. Good questions. Okay. So a subgradient is a vector g that satisfies this equation up here. It extends our notion of what the gradient satisfies for a differentiable function, for a convex differentiable function. And through this lecture, we had a bunch of rules on how to compute subgradients and examples and stuff like that too. So I'm just going to skip through that. This is a very important thing we learned. I wanted to kind of emphasize this again. Subgradients characterize optimality. Right? So a function is minimized at x star if and only if 0 is a subgradient of f at x star. Okay, so this extends the notion of the gradient being 0 for differentiable functions. Okay? So this is true even if f is not convex, right? Because we can define a subgradient to be any value that satisfies this bound, right? 0 is a subgradient if and only if it satisfies this bound. That works for non-convex functions too. Okay, so 0 being a subgradient is also an optimality condition for non-convex functions. But often we just can't compute subgradients for non-convex functions, so it's kind of a moot point. Okay, just to point that out. And we gave an example of a problem. This is like the lasso problem, but where the predictor matrix is identity matrix, right? A is equal to I here. And we claimed that the solution to this problem was just soft thresholding. We just take the components that are larger than lambda, and we move them to 0 by lambda. Otherwise, we set them equal to 0. And we proved that that was indeed a minimizer by looking at the subgradients and showing that when we stick that in to the subgradient of f, we stick in the soft thresholding function for x, then we can choose a subgradient to make that equal to 0. That's all we did. Okay, we learned the subgradient method. That was basically like we did for gradient descent, but we replaced the gradients with just a subgradient. And as was just asked, we're just considering this to be any subgradient. Okay, so we might be in a situation where we don't have control over which one we just get one. And we learned that it wasn't a descent method, so we have to, at each iteration, keep track of what's the best point we've seen so far in terms of its function value. That's what this is doing here. And the difference also between gradient descent and subgradient method was that it's not a descent method. Was that the step size choices were fixed. So either we can take something like a fixed step size ahead of time, or we can take step sizes that were constants that satisfied this condition. They don't sum to infinity, but they don't sum, but they're square sum. This is again a typo. I thought I fixed that in the slides. So this is supposed to say the sum of tk squared is less than infinity, but the sum of tk is infinite. And we learned that with these different choices of step sizes, we can get two different statements. So for a fixed step size, if we assume that the function that we started off with was Lipschitz, and that we were in some bounded set away from the optimum value, that if we use a fixed step size t, then if we let it run forever, we just let subgradient go forever, we can guarantee that we're g squared times t over 2 away from the best function value, where g is the Lipschitz constant of our function. So this is not even saying that subgradient method is going to converge to the optimum. It's going to give us a suboptimal point, and this is the difference in function value at most. Okay, but if the step size diminishes according to this prescription here, then we prove that in the limit we're going to get to a point whose function value is the optimum. Question? No, that's a good question. So anytime that we talk about convergence, we're going to talk about the function values. But if we want to talk about the iterates themselves, that's a different story. And if you think about when we talked about strong convexity, we need some kind of condition like that in order to guarantee that the iterates will actually be close to the actual solution. Right? Because if f is convex, but it's very, very flat, it looks like this, and this is x star, and this is where we are, xk, then their function values can be very close according to our convergence theory, but the actual distance between our iterate and a solution could be very far. Something like strong convexity is going to tell us that this needs to be sufficiently curved, and then we can make statements about xk actually converging to x star. And if you look at the proof of the exponential convergence rate, people call that linear in the optimization community. For gradient descent, in the case that the function is strongly convex, we actually also, in that proof, prove that xk converges to x star. So you want to take a look at that. That's in chapter, I think it's chapter 9 of your book, in Voigt and Vandenberg. That's a good question. Other questions? Okay, so the way we prove this, I'm not going to go through the proof, but I'm going to stop at this point here. We proved that for any choice of step size, ti, at each iteration, subgradient method is going to get us this bound. After k iterations, we're going to be this distance away from the optimum in terms of our function value, where r was the bound on how far our first iterate was away from x star, g was the Lipschitz constant, and these ti were the step size choices at each iteration. Okay, that's what we proved. And then we said, okay, how do we get the convergence proofs from that? Well, let's just plug in ti equals t for every I going from 1 through k. And we get the bound looks like this. And as k goes to infinity, this approaches g squared times t over 2. So that gave us the result for fixed step size. Now what happens if the step size diminished according to this prescription here? Then this bound's actually going to go to 0 because the numerator will go to 0, but the numerator will converge to a constant, right, because this converges. The denominator is going to go to infinity, so the bound's going to converge to 0, right, this bound on the right-hand side. So our function value is going to converge to the optimum as k goes to infinity. Okay, that was a proof from last time. This time we're going to follow that up and say, can we get a convergence rate? In other words, what's the complexity of the error between f of xk best through f of xk star? Okay, and it turns out we can, and the answer is about 1 over root, it is 1 over root k. And if you recall, gradient descent was 1 over k. Okay, so that's an order of magnitude slower than gradient descent. So how do we do that? So let's look at this bound. Right, this bound was r squared plus g squared times ti squared all over 2 times the sum of ti. And now we're going to want to make this on the order of root k, 1 over root k. Because if we can, then we're going to show that the error is on the order of 1 over root k. Okay, so this is a little bit funny, but let's suppose that somebody told you that they wanted an error on the order of 1 over root k, where k was fixed. They said k is 1,000,000. I want an order an error on the order of 1 over the square root of 1,000,000. How do you get me that? I'm sorry, I said that backwards. Let's suppose that somebody said, I'm going to give you 1,000,000 iterations, and we want to try to see how well we can do within those 1,000,000 iterations. Okay, so we're going to consider taking ti to be equal to r over g times the square root of k for all I equals 1 through k. So this is a fixed step size, right? I'm taking the step size to be equal to this for the first k iterations, and then I'm going to stop the algorithm. I'm going to see how far I was away from the minimum.
Get rid of that tension. Right?
Yeah,
Get rid of that tension on
yay. These things are tricky. They have the buttons right in my hands. Okay, so we want to say that we're going to take this fixed step size for k iterations. Okay, and then we're going to stop the algorithm. We're going to see how far away we are from the minimum. So let's plug that in. When we plug that in, we get r squared plus g squared times what's ti squared? It's r squared over g times k. And I'm summing that up from 1 to k, so I get another k here. So these cancel. Right, all over 2 times r over g times root k, and I'm multiplying that, I'm adding that up k times, so again I get a k here. Okay, so the squareds cancel with the r, I get a 2 that cancels with the 2 r's, and I get r g over the square root of k. Okay, so we just said that if we took our step size to be this, and we ran it for k iterations, then the error is going to be like this. Okay, so that's exactly a complexity bound for our algorithm. After k iterations, our error is going to be at most rg over the square root of k. And what you can also do is you can show that this is the best we can do. If we wanted to minimize this bound, if we want to make this bound as tight as possible at each step, then we actually can't do better than this. And that comes from a little bit more arguing. Basically, you say that, well, this is a symmetric function in t, so I have to take t to be all equal to minimize it for any given k, and then we can derive that the minimizer is this, and then this is the best we can do for that bound. Okay, so we can't get better than root k. That's the best the bound can be. If we take ti equals to r over g times the square root of k, we get the bound to be on the order of root k. So we said that after k iterations, this is what our error looks like. Or in other words, the convergence rate of the subgradient method is on the order of 1 over square root of k. Question? How much do I lose if I take tk equal 1 over k for the bound? Well, we can, I don't know off the top of my head, but we can try that. So let's suppose we take r squared plus, so the sum of 1 over tk squared, yeah, I'm not quite sure if we're going to have an explicit formula for that in class. I'm sure we could approximate that. I think that the bound is going to be similar because practical performance is pretty similar between taking 1 over k and 1 over root k. But I'm not quite sure off the top of my head how different the bound is going to be. You can maybe work that out at home. I think you'd have to approximate the sum of 1 over k squared, something like that. Okay, so let's just do a quick back of the envelope calculation. We just said, in other words, that if we want an error on the order of epsilon, we need 1 over epsilon squared iterations. So let's say epsilon was like 10 to the minus 3. So then how many iterations do we need with gradient descent? We need about 10 to the 3 iterations, right, or 1,000, because gradient descent has a convergence rate of 1 over epsilon. But for subgradient method, we need 10 to the 3 squared iterations, which is like 10 to the 6. So that's about 1 million iterations. So that's a big difference, right? 1,000 or 1 million to get an error on the order of 0.001.
So in this case, in this analysis, you took TI to constant, right? This wasn't the same model where K is right.
Oh, I'm sorry. So you were asking about the step size being equal to ti equal 1 over k for all I 1 through k, not 1 over I. Is that right? Yeah. So I think he was asking about this particular step size choice we talked about. Yeah. Okay. So here's an example of subgradient method at work. It's kind of an interesting example because it reveals a pretty famous algorithm for a classic problem. And
then 1 over I squared coming to infinity is bounded by like I squared by 6. So that the numerator stays bounded. The denominator grows as log n, because summing 1 over I for k steps will grow like log k. You get a constant by log c base basically. Instead of 1 by root c, you get a 1 by log c base. So I think that you can actually you get a word.
That sounds right. Yeah, it sounds. So Aditya, one of our bright TAs, just said that if you take the step size ti equal 1 over I, then the rate's going to be, instead of 1 over root k, it'll be 1 over log k, basically. That's why we have our TAs come to class. Okay, so here's this example. It's a pretty classic problem. Let's suppose we have a bunch of closed convex sets, C1 through Cm, and the goal is to find a point that's in the intersection of these sets. All I want to do is I want to find some x star that's in the intersection of these closed convex sets. Okay, so why is that an interesting problem? Let's suppose that these sets described a bunch of equality constraints and inequality constraints, or any types of convex constraints. Okay, these sets could describe. And then I just want to know whether or not those constraints are feasible. So this is like finding a feasible point for an optimization problem, right? I'm not even trying to minimize some function subject to convex constraints. I'm just trying to find a point that satisfies those convex constraints in the first place. So how would we do that? Well, we're going to do that by minimizing a function that we construct whose minimum is going to tell us whether or not there's a point in this intersection. And we're going to minimize that function using the subgradient method. Okay, so let's first define the function f of x to be the maximum over all I from 1 to m of the distance between x and ci. Okay, so what's the distance between x and a set? If you've forgotten, or if you haven't seen that notation before, it's just equal to the minimum of x minus u, of the distance between x and u, subject to u being in that set. Okay, so it's the closest we can get to x if we have to stay in the set C. That's what the distance means. Okay, so f of x star is equal to 0, right, if and only if x star is in all of these convex sets. Right, if it's 0, then this was 0 for each I. In other words, it was in every convex set. Okay, so we're going to try to minimize f, see if we ever get to a point for which f of x is 0. If we did, then we have a point that's in the intersection of those sets and we win. If we don't, if we minimize it and it's bounded away from 0, then we know that there's no point in that intersection. Okay? So if C is closed and convex, then there's a nice thing about it being convex. The nice thing is that there's a unique point, and we write this as the projection onto C of x, u star, right? So that unique point minimizes x minus u over u and C. Okay, if C is convex, then there's only one point that can achieve the minimal value here. I'll let you think about why that's true maybe at home on your own time. So we can write the distance between x and C as the distance between x and its projection onto C. Okay? So now we want to figure out how to calculate subgradients of f. Because if we can calculate subgradients of f, then we can apply subgradient method, and we'll get an algorithm for trying to find a point in the intersection of those convex sets. So how do we do that? Well, the first thing is that we want to figure out how to calculate a subgradient of each fi. F is a maximum of functions, so let's first try to figure out how to calculate subgradients of fi. So here I actually wrote down that the gradient of f was something, fi is something. It turns out that fi is differentiable in this case, but maybe for reasons that are a little bit beyond what I wanted to talk about this class, it doesn't matter. We're just going to calculate a subgradient of fi. It'll be the same thing. Turns out there's only one, and it's differentiable, but like I said, that's a little bit beyond this class. So I claim that for each I, if I take a point that's not in the convex set, so fi of x is not equal to 0, then x minus its projection onto C divided by the norm of that difference is a subgradient of fi at x. Okay, so can anybody see why this would be true? If we just did something very sloppy? Yeah.
So is fi possible on the boundary?
On the boundary?
Yeah, for x on the boundary.
No, on the boundary of C. Oh, is it differentiable for x on the boundary of C? No, because then it's, I mean, yeah, it'll be 0.
The function is differentiable everywhere except the boundary. It's not differentiable everywhere.
It's not differentiable for points inside C either. Because then,
0.
yeah, so it looks like,
Why is it
No,
not?
it's a flat 0 inside C, right? So it's differentiable inside C.
oh, it's not differentiable on the boundary of C. Yeah, you're right. Right. So, I mean, the point that the reason I'm taking x naught in C here is not because it's not differentiable within C, but because we're going to need to compute derivatives or subgradients of this function throughout the algorithm. But if it ever was inside C, we wouldn't be taking its subgradient or its derivative. Because of the max rule, we take the one that's farthest away, the one that has the largest function value. Right? If it was in C, it would have a 0 function value. And if they all have 0 values, the algorithm would be over anyways. So we only have to consider points that weren't in the set to begin with. Was there another question? No? Okay, so if we did kind of a sloppy chain rule, right, and we just plugged in, or actually no chain rule, if we forgot the chain rule, and we just plugged in the projection of C, we just took this right here, and we differentiated this with respect to x, and we forgot the chain rule, then we'd get this. Right, but there's something missing here, which is the derivative with respect to x of this projection. So that's kind of a hard route to go. So that's why I didn't really want to cover that. And we're going to actually just take this point, and we're going to show that it's the subgradient of fi at x. From the definition directly. We're just going to go for it. Okay, so how do we do that? So we're going to start off by recalling that by the definition of this projected point, and I'm going to call this u just because I don't want to keep writing the projection over and over again. It's true that x minus u transpose y minus u is non-positive for any y in the convex set C. Okay, so why is that true? Well, let's draw a picture first and just convince ourselves that makes sense from the picture. Let's suppose that was x, and this is C, and I projected it onto C, and I get that point u. Right, then this is the vector x minus u. Do I have that backwards? Yeah, right, sorry. And I take any point within C, call it y, and that's y minus u. Then no matter where I take y in that convex set, the inner product of these two vectors will be non-positive, right? This is where it's going to be 0, and where it's positive, y can't be in the set. You can imagine that's true because C is convex. Okay, so how do we get this inequality? How do we prove that? Well, let's just look at this function, x minus u squared. We can think that, right, the projection of x onto C minimizes this function, we can also write that as the indicator function of C here, of U, and get rid of the constraint. Okay, so we want to figure out which point minimizes this function. We can take a subgradient of this function and set it equal to 0, and that'll give us the an optimality condition for what this projected point should satisfy, and then we're going to get this right out of it. So let's do that. We can put a half here, it doesn't matter, right, to make the gradient easier. So the gradient of the first term with respect to U is U minus x. Right, the second term gives me actually the normal cone of C at the point U. Okay, so I know that when I stick in the optimum U, this must be true. Or in other words, I have that x minus U must be in the normal cone of C at U. Okay, so what does that mean? It means that if I take x minus U, right, and I take the inner product of that with U, it has to be bigger than or equal to x minus U, and the inner product with y for any y in C. That's what the normal cone means, right? That's what this means for this to be in the normal cone. And if I just rearrange this, I get that U minus x, or how did I write it in the last slide? I want to write it like this. X minus U transpose y minus U is non-positive. Okay, so that matched our intuition with this picture here that we just drew. Okay, so that's true for any y in C. So we can certainly say that C is actually contained in a half space, and that half space is equal to the set of all points y for which this inequality holds. Okay, so let's just redraw that picture real quick. There was C, here was x, here was U, and this is the half space I'm talking about. That's not a very good perpendicular. Okay, but this is the half space here. This is H. And we just said that C was contained in H. That's what that argument showed. Okay, so now I claim that the distance between y and C is bigger than or equal to x minus U transpose y minus U all over the norm of x minus U for any y. That's my next claim. Okay, so we have to check this for two things. Let's check it for y in H and y not in H. So for y in H, well, the right-hand side for y in H is actually non-positive. Right? Because by definition, H was a set of all vectors y for which this is non-positive, so this is going to be clearly less than or equal to a distance, so we're fine. Yeah, question?
I didn't understand the relationship between the normal cone and the hyperplane.
Between the normal cone and the hyperplane. Well, there wasn't quite a relationship to the normal cone and the hyperplane, but we derived this inequality. The normal cone is just this, actually. That's all it is for this convex set in particular. That line there. The hyperplane is the set of all y for which, if we look at the distance between the difference between y and u and x and u, that inner product is negative. So it's everything that lies below this line here. This is a supporting hyperplane to the convex set C. Another question?
So one relationship between the normal cone and the hyperplane is that every vector in the normal cone is a normal of a hyperplane that supports C. right? So that's, it's not necessarily true that H is defined by any particular vector in the normal cone, but could have used any one.
Yeah, in this case there's just one, so it is, but
Right,
yeah.
so it is, yeah.
Did everybody get that, or do you want that to be repeated? Okay, so this is what we're trying to prove right now, because this is going to basically tell us that what I'd written down is actually a subgradient of the distance function. And we've just said that for y and h, we're good. Let's say y not in h. So for y not in h, I claim that this is actually equal to the distance. The right-hand side is just the distance between y and the hyperplane. And in that case, it's certainly going to be smaller than or equal to the distance between y and c, because c is contained in h. Right, so if we can prove that, we're also done. So why is that true? We can maybe go to the picture. It helps to look at the picture. Let's take some y out here. Okay, so I'm looking at the inner product between these two vectors. The inner product between these two vectors is equal to x minus u. Right? If I have x minus u transpose y minus u, that's equal to the norms of those two times the cosine of the angle in between them. Right? If theta is this angle here in between those two vectors. Okay, so I can also write that as if this angle here I call phi, I can write that as x minus u times the sine of phi. Okay, so let's keep this picture in mind, and now go back to this expression here. If I just plug in what we just computed, right? Yeah, thank you. Sine phi. Then these cancel, and I get the norm of y minus u times the sine of phi. Well, what's that in this picture? That's exactly this distance right here. That's just the distance between y and the hyperplane. Okay? So, that's right. Okay, so now we've proved this inequality. Right here. I guess I'm shifting it wrong. And now from just basically rewriting that, we can prove that what I wrote down is actually a subgradient. So let's just rewrite that slightly. We've proved that the distance between y and c is larger than or equal to, let's write x minus u transpose y minus x plus x minus u over the same denominator. Okay, and now let's just split that up, and I get the first term is just x minus u. That's the distance between x and c, right, because u was the projected point, plus x minus u over its norm transpose y minus x. All right, that's exactly the equation for a subgradient. So that's all we're saying is that, look, this thing right here, which I'll call g, that's indeed a subgradient of the distance function. This is a subgradient of the distance function of x at c. Okay? Questions about that? Do people believe that now? All it requires is a bit of kind of geometry. Yeah? The steepest direction.
Yeah, if you want to go from that point to this comment, the fastest path is projection. And that's all is exactly
Yeah, but I don't know why that would tell me that's the gradient. Like informally that makes sense, but I don't know why that would tell me that's the gradient vector directly. We don't really have rules, at least not yet, of taking gradients or subgradients of minima of convex functions. We know how to take subgradients of maxima of convex functions. But I'm not quite sure how I would use that argument to get this. You can think about it and we can talk about it after lecture if you're still interested. Okay, so now we've just proved on the slide here that this is true. Well, we've actually proved this is a subgradient of Fi, and I've been a little bit cheap, and I've written down that it's the gradient, because that's also true. But that's not important for the purpose of this argument. And now we're going to use a rule that we learned last class from the subgradient calculus, which is that if f of x is equal to the maximum of a bunch of convex functions, right, then the subgradients of f at x, they're equal to, or yeah, the subdifferential, the set of subgradients, is equal to the convex hull over the union of all j, such that fj of x is equal to f of x. So I take the functions that are active, that achieve the maximum, and I join their subdifferentials. Okay, so in particular, if fj is one of the functions that's maximum, I can just take a point in its subdifferential, and that is a subgradient of f. Okay, so that's all I'm doing in the second step. I'm saying that if I happen to have a function such that it actually achieves the maximum, and I didn't want that maximum to be 0, because we only derived subgradients when x was not in the set. But again, this is not important, because if this is ever equal to 0, we're going to stop the algorithm. We wouldn't be computing subgradients in the first place. Then I can just take this to be a subgradient of f at x. Okay, that's just from that rule. Okay, so now we actually have a prescription for computing subgradients of f. What do? We find a set that it's farthest from, that the point x is farthest from, the distance is the largest. We project that point onto that set, and we divide by the difference by its norm. That's a subgradient of f. Okay, so now we're good. We can run subgradient method with this prescription for computing subgradients. I'm going to use something that's called the polyak step size, not because any other step size would be bad, but only because with this particular choice of step size, we're going to actually get a famous algorithm out of subgradient method. Subgradient method is going to turn into something that's quite intuitive. Other step sizes would work, but I just wanted to show you that a particular famous algorithm is a special case of the subgradient method, when we take this step size and this subgradient. So in that case, this tells us to take tk equal to the function value of f at xk. Okay, that's not the full Polyak rule. I actually gave you a reference at the end of this lecture if you wanted to look it up, but that's what it looks like when we apply it to this problem. Okay. So now let's go ahead and let's just derive the update rule for a subgradient method. It looks like this: xk is equal to xk minus 1 minus tk times the subgradient. Well, actually, I think I maybe wrote this slightly wrong. I would like to take tk to be equal to the function value at the previous iteration. Okay, so that's the step size tk. What's the subgradient we're going to take? We're going to take xk minus 1 minus the projection onto ci of xk minus 1 over its norm. Where xk minus 1 is farthest from ci. That's how we choose that set Ci. Okay, that was just our subgradient rule. But now, let's look at this. Fxk minus 1 in the denominator here, the function value at the previous iteration, it's equal to the maximum distance of xk minus 1 to all the sets. Look, we chose Ci because it had achieved the maximum distance. I must have turned the light on. Hope you can live with that. Is that still good? So look, these are exactly the same by definition of Ci. So what's the update rule? It just looks like xk minus 1 minus xk minus 1 plus the projection onto Ci of xk minus 1. From that, these cancel. So the update rule is actually I just take xk minus 1 and I project it onto the set that it's farthest from. And that gives me xk. The next step, I find the set that that's farthest from, and I project that onto that set, etc. So this is called the alternating projections algorithm. If I just have, for example, two sets, then all I'm doing is I'm projecting onto one set and then the other repeatedly. Okay, so this is a picture of what this looks like for two sets. Suppose I start out here, and I'm farthest from C1, then I project onto C1, that gives me x1. Then I'm definitely farthest from C2 because I'm in C1, so I project onto C2, and then onto C1, etc. And I keep doing that until I find a point in the intersection. So if somebody gave you this algorithm and they said, prove that this converges, you probably have a pretty hard time thinking about why that converged. In the context of this particular problem, it looks like maybe you'd use some kind of geometry or some other kind of arguments. That wouldn't be trivial, right? And also, if somebody asked you how fast that converged, that would also be a difficult question to answer. But all we've done is we've established that this actually is a special case of the subgradient method, so we know it converges, and we know its convergence rate. So that's one of the nice things about studying these generic methods, is that we can actually say a lot of things, in particular about different algorithms that happen to be special cases of those methods. Yeah? Yeah, right. So we want to find anything in this intersection here. Anything in there is a solution. Yeah, you're right. This particular algorithm is neither fixed step size nor is it diminishing. But the Polyak step size, which I gave you reference to at the end, this actually converges, just like diminishing does, at the same rate. It's just Polyak step size is only used when you know what the optimum value should be of the function. So if I know what f of x star should be, I can use the Polyak step size. And in this case, the optimum of the function value is going to be 0. If we know they have a point, if we know that they have a feasible point to begin with, the optimum is going to be 0. So there's a step size prescription for tk, and we have to use f of x star in here, but you don't see that up here because it's 0 in this case. Question?
What if physical solution is only one point?
Yeah. It still converges, so that's a good question. So there's actually, if you're ever going to use this algorithm in practice, there's some kind of practical considerations here. So even if the feasible region was even non-singular, if there was a bunch of points in here, we're not going to actually ever find a feasible point, you might argue. We're going to get, in the limit, we're going to get a feasible point, but if we stop the algorithm at any particular iteration, we're not going to have a feasible point x star. Right? Because we're not going to have f of xk necessarily equal to 0 for some k. We're guaranteed that in the limit it'll be 0, but not for any particular iteration. So how do we get around that? How do we actually get a feasible point if we want to actually use this for something like a starter for a convex optimization problem? We would have to take closed convex sets that lie in the interior of each of our convex sets. We'd peel them back a bit, hope that their intersection is still not empty, and then we run the algorithm. And at some point, if we find a point in the intersection that's close enough to the intersection of these peeled back convex sets, we'll get a feasible point to the original problem. We just have. What's that? That's still a heuristic. Yeah, I don't have a convergence rate for that, but in practice, if I peel them back just slightly, I will get a point. If the intersection is non-singular, if it's not just one point, then these two will still intersect non-trivially, and I'll converge to a feasible point in a finite number of iterations, at least. Good questions, very good questions. Okay, so this is what I was alluding to a little earlier. We talked about the worst case bound for gradient descent. We can also say something similar for subgradient method. So what's the strength of the subgradient method, first of all? Its strength is that it's broadly applicable. As long as we can compute a subgradient of a function, we can apply subgradient method. And for most convex functions you're going to run into, either in this course or beyond, you'll be able to compute a subgradient. I mean, it might be difficult at the start to learn subgradient calculus. Once you get past that, you should be able to compute subgradients of most convex functions that you run into. So you can apply this method, and it'll do something. And that something, you know, it may or may not work for your particular application, but it'll give you something that will at least, in principle, minimize the function at the rate of 1 over square root of k. Okay, what's the downside? Well, the downside is that this rate is actually really slow. It's an order of magnitude slower than gradient descent. Gradient descent, we said, itself wasn't even very good. So this is really slow. So you might ask, for a generic non-differentiable convex minimization problem, can we do better? Is subgradient method just kind of doing all right, or can we do better? And the answer, I'll spoil the answer, is no. We can't do any better. So this is actually achieving, for a pretty broad class of problems, the optimal rate for minimization. And let's see what time it is. Yeah, I think we're going to go ahead and prove that today in class. So what are the problems that we're considering? Let's consider the following setup. You give me a starting point x0, and I'm going to look at all convex functions that have a solution at some point x star, for which the distance between x star and x0 is bounded by r, by some number. So it can't have a solution off at infinity somewhere. And f is Lipschitz with some constant g on this bounded set. Okay, so these were exactly the functions for which we could apply subgradient method, and it gave us a rate of 1 over root k. So we're going to look at the same problem class. And we're going to consider that we have something called a weak oracle. It's also, some people call it a resistive oracle. And what happens is, you give this oracle an x, and this oracle gives you back a subgradient of f at x. We don't know which one. It can give us back any one. So this is trying to be in a situation where we might not be able to compute strong subgradient calculus. We can't compute all the subgradients, so we're just going to say that this oracle gives us back some g. It's a valid subgradient, but beyond that we don't know which one it is. And we're going to try to see, with this setup, how well we can do in terms of a convergence rate. What are the methods we're going to look at? We're going to look at first-order methods, but they're going to be non-smooth first-order methods. So it's just like a first-order method we talked about last time. It's an iterative method, but now it updates the kth iterate to be an x0 plus the span of the subgradients it's seen, not the span of the gradients. That's all it is. Okay, and these subgradients come from the weak oracle. So g0 is a subgradient of f at x0 that the oracle gave us. Okay, so subgradient method is indeed a non-smooth first-order method, right? It does actually obey this update rule. So here's the theorem. It's a familiar name here. It's the same guy who gave us the theorem for the gradient descent case. The theorem says that for any k that's smaller than or equal to n minus 1, and any starting point x0, I can find you a function in the problem class for which any non-smooth first-order method has function value away from the optimum bounded by something like 1 over root k. Okay, there's some constants here, but the order is the same. You can't do better than the rate 1 over root k. And subgradient method is getting us that rate, so we can't hope to improve upon it for general convex non-differentiable minimization problems. So the proof is actually quite simple. It's quite simple when you consider the case k equals n minus 1 and x0 equals 0. So I'm going to do that because I didn't want to go through a very difficult proof. The general case follows also. Okay? So we're going to, like I said, consider x0 equals 0 and k equals n minus 1. So we're going to see, with those choices, how well can any non-smooth first order method do for a particular problem. And what problem is that going to be? We're going to look at this following function, f of x. It's going to be equal to the maximum of the components of x plus 1/2 times the norm of x squared. Okay, that's a perfectly reasonable convex function. It's not differentiable because this is not necessarily differentiable at points where xi is equal to xj for two different components. Yeah. So the first thing I claim is that the solution itself, or a solution rather, is given by the vector where I take minus 1 over n in each component. And the optimal value of the function is minus 1 over 2n. Okay, so why is that true? You're starting to see a pattern here. We just take subgradients of this, and we see when those subgradients are 0. I told you what a guess what this for the solution was, so we're just going to plug that in and see if we can make this a subgradient 0 of f. Okay, so what do subgradients of f look like? Well, they're just going to be, let's say, v, which is the subgradient of this max term plus x, right? And I want to make that equal to 0. And again, we have some rule for what subgradients look like of this maximum function. I look at all the components that achieve the maximum, and I can take any point in a subgradient of one of those components, and I can take their convex hull, and that gives me any valid subgradient of this function here. Okay, so if I look at x star, this point right here, look, every component of x star achieves the maximum. So I can take, in particular, this point, right? 1 over n, comma, dot, 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 1 over n each component, because the subgradient, for example, at x1 is 1, and the subgradient of each component is 1, and they're all active. So look, this is a point in the convex combination, the convex hull of these vectors. All right, so that's a valid subgradient at x star, according to that rule. And right now I plug in I'm going to add x to it, because that was the second part, which was minus 1 over n each component, and that gave me 0. So I just indeed proved that x star minimizes this function f, because I was able to find a subgradient of f at x star that was 0. Okay, now what's f of x star? F of x star is equal to, well, the first part's minus 1 over n, because it's the maximum of each component. That's just that. Plus, the second part's going to be 1 over 2n, right, because I get 1 over n squared in each component. I add them up n times. I get this. So the optimal value is minus 1 over 2n. Okay, so what I wrote down here was true. Okay, how do we check that, for example, f is Lipschitz with constant g equals 1 over 1 plus root n on the set of all x such that x has norm at most r, and I'm going to choose r to be 1 over root n. That's what we want to check next. Well, that's actually, there's a couple ways to do that. We can actually try to plug in function values for f and bound it by this g times the difference in the arguments. That's going to be kind of hard. Let's just actually bound the norms of the subgradients of f. Right? We also argued that was equivalent to bounding to getting a Lipschitz constant for f. How I guessed it? I got this because I wrote the lecture notes. I didn't actually give you a prescription for computing X star. I just told you that this is the optimum, and we checked that it was true. So I didn't actually tell you why I thought that was the solution in the first place. But yeah, that's a good question. Is it unique? I don't know the answer to that. Probably not.
I think it is functions.
Oh, I'm sorry. Yeah, you're right. So this part makes the function strictly convex, right? Since we're adding a quadratic to it, so it is unique. Thanks, Jeff.
So another, like if you want some intuition for how you might guess that, well, you can see it's symmetric in the components of X, and so you would guess that it's going to be the same, each component of X is the same. Then you plot it in one dimension and look where you think the minimum is, and guess and check.
Okay, so what are the subgradients? Right, we said subgradients are anything that looks like this. They look like V plus X, where V is in that convex hull. V is in the convex hull of, I can also write it like the convex hull of E1 through En, those the standard basis vectors. And let me just look at the norm of this. And if I bound subgradients and norm, that's equivalent to getting a Lipschitz bound for F. Okay? And that's by the triangle inequality, that's smaller than or equal to V plus the norm of X. Right? And well, V and norm can be at most 1. If it's in that convex hull, I can take it to be one of the points on the vertices of that convex hull. That's the largest I can do. And X, I assumed, was bounded in norm by 1 over n. Right? Because I considered only X in this set, the set of all X for which its norm was at most 1 over n. That was my R. So this is our Lipschitz bound right here, G. Okay, so that was a lot easier than actually going to the function and trying to do something like this. Prove that f of x minus f of y is bounded by g times x minus y. That would have been much more messy because of the form of f. A lot easier to actually just look at its subgradients and bound them. Okay, so now we have all of the things that we're looking for. We have g, we have r. We know the optimum value is, write it down again, minus 1 over 2n. Okay, and now here's the setup. The oracle is going to give us the following subgradient. It's going to give us g equals ej. This is the jth standard basis vector, so it has 0 in all components and just 1 in the jth one, plus x, where j is the smallest index for which xj is equal to the max. Okay, so that's a totally legitimate subgradient. It's just going to be difficult in this particular situation to minimize the function with this prescription of the oracle. Okay, so it's going to just look at all the points that achieve the maximum, give us the take the smallest index that achieves the maximum, and give us a subgradient according to that. Questions about our setup so far? Okay, so now I claim that if you used any non-smooth first-order method, then after I iterations, for any non-smooth first-order method, we're going to have x, the ith iterate, having components from I plus 1 all the way to n equal to 0. No matter which one we use, that's going to be the case. So why is that true? Well, G0, right, if we start at 0, the first subgradient we get is just going to be equal to E1. Right? It's going to be Ej for the smallest j that achieves the maximum plus x. X was 0. 1 is the smallest index that achieves the maximum because the maximum is 0. It's all 0. So that's what we're going to get for the first subgradient from our oracle. Let's look at the next step. I claim that the span now of G0 and G1 is contained in the span of E1 and E2. Okay, why is that true? Well, any method now, it's going to update, any non-smooth first order method, it can update the point x1 to be in this, right? Because x0 is 0. So that's all it can do, is it can choose some point in there, and that's what x1 is going to be. Question? E1 is a vector. E1 is a vector with 1 in the first component and 0 is everywhere else. Okay, that's the notation I'm using. This is, usually people call this the jth standard basis vector if it has a 1 in the jth component and 0 everywhere else. It's a subgradient of the function because the function of at x0 equals 0, remember that's what we were starting off with. If we look back at the function, let's look back at the function. This first term, every coordinate here of xi achieves this maximum because it's all 0. So I could have chosen a valid subgradient is ej for any j. It's actually anything in the convex hull of all those ej's. But my oracle gave me the subgradient corresponding to the smallest index that achieves the maximum. In that case, that was just 1 because it achieved the maximum. And I guess I wrote it down on the other piece of paper, but no, here I wrote it down right here. See, it's ej plus x, but x0 was 0 here. That's why it's a subgradient of the function. Okay, so why is this true? Okay, so what can subgradients look like? So G1 is now a subgradient of the function at f of x0, right? Can anybody reason for me why this is true? All right, so this looks like some v0 plus, sorry, at x1. Okay, so where did x1 come from? X1 is just in the span of G0. Right, that's all non-smooth first order methods are allowed to do. So now let's look at what G1 could be. It's anything that looks like a subgradient of f at x1 plus x1. Okay, well x1, we just said that it has to be in the span of G0. That's the span of the first standard basis vector. So it's 0 for components 2 through n. Okay? And this is going to be either E1 if 1 achieves the maximum, or it can be E2 because let's suppose that the first component of x1 was negative, then the smallest component that achieves the maximum is x2 because it's 0 for 2 through n. So this can be in the span of E1 and E2. This can be in the span of E1. So the span of the first two subgradients have to be contained in the span of E1 and E2. If I happen to make the first component of x1 negative, then it would be something with E2. Otherwise, it's just something with E1. Okay? So now what happens is if I continue that logic, I can just argue that after any number of iterations, the span of the first I minus 1 subgradients that I see is contained in the span of the first I basis vectors. Okay? And because any first order method updates in this span, it has to be 0 for components I plus 1 through n. That's why this claim right up here is verified. Okay, so now let's look at f of x n minus 1, the point after n minus 1 iterations. Remember, we were taking k to be equal to n minus 1 because it made the proof simple. Then that's at least 0 because the nth component of x is 0. Right, so the max is at least 0. And then the second part of f was just the square term here, this 1/2 norm of x squared. So after n minus 1 iterations, the function value can be at least 0. It can be larger than 0 too. So what's the difference between x minus the nth minus 1 iterate and the minimum value of the function? That's at least 1 over 2n, right? Because f of x star was minus 1 over 2n. And now if we play around with our constants, see if I can play around with this piece of paper so that it shows up on the screen. You can see that was actually just exactly Rg over 2 times 1 plus root n. Okay, so that proves this for the case where k was equal to n minus 1 and x0 was 0. So we said that any non-smooth first order method can achieve an error at best this after n minus 1 iterations. And the proof for arbitrary k and x0 is very similar. Other questions about that? Yeah. Right, but that's all I need to do, right? If you look at the theorem, I just told you that if you give me any k and any x0, I'll find you an f that makes the problem hard. So if we change k and x0, like if the proof for an arbitrary k and x0, we'll have to change f to make that work. It seems maybe like kind of a cheap proof, but it's a proof by counterexample. It's an impossibility result, right? So all I need to find for any x0 and any k something that makes it hard. It's very similar with your homework if you're working through that problem. You're just constructing a specific function that makes gradient descent hard, or a class of functions, because for your homework you're considering an arbitrary k. Yeah? So the method is similar, but what we can say about the method is pretty different. In gradient descent, we had that the gradient of f was Lipschitz. So it provided us with this upper bound, a quadratic upper bound on the function. And if you look back at the proof, that's what enabled us to kind of, for that particular proof, enabled us to prove the 1 over k rate. Because we took a step size that was smaller than or equal to that Lipschitz constant, and we got that the function descended by something like the previous iterate minus a quadratic in the gradient.
So the only assumes that the function would Lipschitz, that is, if gradients are bounded or gradients are bounded.
Yeah, we get the same rate. Yeah.
Just made a stronger assumption that even the subgradients, so basically even the gradients were Lipschitz at that point.
Right. But the point that we kind of talked about last class, that does not make sense to talk about subgradients or functions that have Lipschitz subgradients. You can't really do that here. So this is an appropriate assumption for the setting we're looking at.
But if you have to say the function is always bounded by the function quadratic, then you just prove it? Would that be the case? Or
We want it to be bounded above by a quadratic. Its subgradients to be bounded above by a quadratic for gradient descent. I mean, the trickiness with subgradient method is that part of the trickiness is that we don't know which subgradient we get, right? So we have to make statements that apply to all subgradients of the function. And that's why this Lipschitz condition here made sense, because it's just saying that we're going to bound all subgradients by some constant. If you want to think about a method that took a particular subgradient, you might be able to place stronger assumptions on f and prove a stronger rate, but I'm not sure how widely applicable that would be to practical situations. These are all very good questions. Okay, so that basically finished up our lecture on subgradient method, and now we're going to turn to what to do next. Okay, so we just said that basically we're doing the best we can for a generic non-differentiable convex minimization problem. So what do we do next? Do we just kind of throw in the towel and say, okay, let's move on to second order methods? Well, no, we can actually do a lot better if we look at a smaller class of problems. So there are many ways to improve kind of general non-convex problems. These go beyond first order methods, so you can do things like localization methods. You can use things like filtered subgradients. You can also use something like a memory term. We're going to see that in a couple of lectures, what memory terms look like. But these don't really provide substantial improvements to the subgradient rate of convergence. They just tend to be kind of marginal improvements. And the reason why they can't help that much is because all of these methods are trying to apply to any non-differentiable convex minimization problem. So we're going to focus on something a little different. We're going to say, let's now just focus on particular convex minimization problems that aren't differentiable. And hopefully, for a smaller class, we can do better. And hopefully that class is broad enough that it still contains interesting examples in it. So let's look at functions of the form g plus h. So we're going to split up f into g of x plus h of x, where g is convex and it's differentiable. So this part is nice and smooth. And h is convex also. Doesn't need to be differentiable. But we're going to try to look at functions h that are simple. Okay, so we can have a complicated smooth part and a simple non-differentiable part. Let's see if we can do well for that class of problems. And it turns out that we can, actually. We can recover the 1 over k rate of gradient descent with a very simple algorithm. It mirrors gradient descent very closely. And this has very big practical consequences for a lot of important problems, because a lot of important problems we want to solve in statistics and machine learning, they have simple non-differentiable parts and complicated smooth parts. So this prescription is going to work. Okay, so that's what we're going to start with today. Today is over. I looked at the clock. Well, now you have a great lead into next time. So get excited for Thursday's lecture, because that's what we're going to do.